So today we're going to talk about how similar triangles and proportions help us in real life. All right, so get your mind away from similar triangles, and now we're just looking at specific examples of how these can work to our advantage. If I have the height of a giraffe and the height of a person, and the shadow lengths, I can find the height of the giraffe. Okay, I can use this concept of proportions to say the height of this person is proportional to the height of the giraffe because the shadows are proportional to each other. All right, so now we plug in some numbers. We look here and we say we've got 5 compares to height of the giraffe as 8 compares to 22, or we could look at it the other way. Either way, we see we've got some similar triangles going on, and now I can look at this and say I can set it up however I want to. But for me, I'm going to go with 5. Let's go with 10. So we got 5 over x is equal to 8 over 22. We can reduce this down by 2, so we get 4/11. We cross multiply, and I get 4x is equal to 55. And then I divide both sides by 4, and I get x is equal to 55/4. Okay, and I can leave it just like that. I could approximate, I could get to a decimal value, but I don't accept decimals, I don't accept mixed fractions. So your answer is 55/4. And this cross product we've been doing for a while. You learned it in 9th grade. Now we're just looking at specific ways to set it up with geometry and real life application. Now go ahead and answer your essential question. What real world problems can we solve using known measurements? We can heights, shadow lengths, distances, things like that. So here we have another shadow length example. The height of the tall building is unknown. The height of the short building, we know it's 30 feet. The shadow length here for the tall building is 50 feet. And the length here is 10 feet. So when I cross these off, I can reduce this fraction down, and I'm left with x over 50 is equal to 3/1. So then I cross multiply, and I end up with x is equal to 150 feet. Check that out. That was it. I set up my ratios, set them equal to each other. I recognize these are fractions, and I cross multiply, and I'm done. Now, oh, here's another height and shadow. We've got the height of the girl we don't know, but we know the palm tree is 20 feet tall. Let's see, that doesn't go there. The shadow of the girl is 3 feet. The height of the tree is 20. The length of the shadow is 15. So we can reduce this down to be 4/3. And this is still going to be x over 3. Cross multiply. And I end up with 3x equals 12. Divide by 3. Divide by 3. X equals 4. I'm doing these for you. You should be able to do these on your own on the test and on homework. So now we're going to talk about a new topic, directly proportional to. If you hear those words in a sentence, that means that you've got a problem that can be set up with a proportion, right? Directly proportional. Imagine how we can use proportions in this question. So you'll have a problem like this on the test, so I want you to be ready for it. If it says a force required to push a bus is directly proportional, that's what I'm looking for. And when it says directly proportional, I can say F for force is directly proportional to the distance the buses move, D. That's what I get out of that first sentence, F over D. Okay? So now we can look at this a little bit differently. We can say, okay, so I've got the force is proportional to the distance. And that gives me force and distance. Now we look at our first bit of information, and I've got a force of 415 pounds. Notice how force is on top, and the force of the first example is right here. So that much pounds moved the bus 5 feet. Now I want to know how much force would move the bus 83 feet. So I'm just setting it up as a proportion. Force is on top, distance is on bottom. I cross multiply, and I set it up. Okay. If you want to do a table of values, that's fine. I just want you to notice that in that table of values, we've got a fraction that I can cross multiply on, and I can get my answer. Ooh, 415 times 83 divided by. I'd rather not do this multiplication if I can avoid it. So I'm going to divide by 5 first to both sides. Feet's all cross off, and now I notice I've got 415 divided by 5. Well, I know that's divisible by 5, so I can reduce that down to be 83. And now I have 83 pounds times 83 is equal to X amount of pounds. That multiplication I can do. Now on a test, multiple choice, you can approximate. I could say 80 times 80 is 6,400. Well, I know it's got to be bigger than 6,400 pounds, so I can find the multiple choice answer that's bigger than 6,400 pounds. But in real life, you would just do 83 times 83, and that's just long multiplication. Totally doable. So that's one. Now we've covered two different concepts. The height of a building or the height of a giraffe or whatever, based on the length of the shadows. And we've talked about is directly proportional to. And that's going to be forces and distances, or the amount of cookies you eat based on how much I weigh. You know, if I weigh 300 pounds, then that means I eat 9 cookies, which would be kind of cool as a kid. My mom always told me that you only get 3 cookies no matter what. But I thought that it was unfair because I was a little kid, so I should get more cookies. Didn't work out that way. So if we look at this one as this is a new concept, this is a new topic of discussion. It's the triangle proportionality theorem. So if I have 2 parallel lines that cut a triangle like this, okay? I've got triangle RQS, and I've got TU is parallel to QS. If that happens, then I can say that these two sections are proportional. RT and TQ and RU and US. Okay, this is the triangle proportionality theorem. It's only based on if I have parallel lines here. All right, now there's more information going on here that you're not informed of, but actually all of the, yeah, it's pretty awesome. There's more going on here, but all we're talking about today is just this ratio, RT, TQ, RU, US. And that only works when there's parallel lines. Right here, I've got parallel lines set up in this pattern with the triangle being cut by one of the parallel lines. Now if I look at this whole side length here is X, and this top part is just 15. So I need to know how big this section right here is. Well, the whole length is X, and then I take away 15 from that. Remember the takeaway means subtraction? So I put in here, I got X minus 15, and that's the length of that small piece. Now, I know that this is proportional. I can set up my fractions. That's what this line means right here. If you look at this fraction, 20 over 15 is proportional to 8 over X minus 15. Now, that's not the way it's written here. The way it's written here is RT, TQ, and RU, US. So this reads 20 over 8 is equal to 15 over X minus 5. But I just did the interchange means, and I switched it to here. The reason I did that is because I want 20 over 15 because this reduces nicely. So if I reduce down that fraction now that I've done the interchange means, I can get 4/3. Now I can cross multiply, and then I can divide by 4 to both sides, or distribute, however you want to do it. I would have divided by 4 first, but that's just me. Either way, you add 60, you divide by 4, and you end up with X equals 21. So calculate the value of the variable. We're done. If it had said give the side length, then we would have had to plug it back in and solve. But since it just asked for the value of X, we're done. And we wouldn't have been able to find that without knowing these proportionality theorems right here. Now remember, you can always do the interchange means test. So RT over RU is equal to TQ over US. That's totally fine to do that. Just whatever helps you best get the answer. So now we look at the converse of that. If instead I told you that RT over TQ is equal to RU over US, you can then deduce that QS and TU are parallel. before we talked about ways of proving lines are parallel using angle pairs. Notice how if this angle and this angle are congruent, that makes them corresponding angles. That makes them parallel. Well, now we've got a new way of showing they're parallel. RT/TQ, RU/US. And if that's true, they're parallel. So if I give you a problem like that, you'll be able to handle it. This is the next one. We've got another concept. This is a new topic, new concept. Wrap your heads around. If there are three parallel lines and they intersect two different transversals, then they divide the transversals proportionally. So that would mean that if these three lines are parallel and they intersect all these two lines at different places, then we've got UW and WY and VX over XZ, or flower over smiley face. Wait a second, smiley face is VX. Notice how I did the interchange the means. I switched them. Okay, you can do that. Be comfortable with that, because it's not always going to make sense if you do it the other way, and it makes it easier to reduce your fractions. So either way works. As long as I'm doing the interchange the means test, I'm good to go. So let's go ahead and go on to the first problem. Now, notice three parallel lines. For me, it's easier just to look at it like this. Draw my little division symbols, and I'm done. Notice how I'm setting up my fractions here? That's how I do it. And it happens to work out really nicely this way, because then I set it up and I can reduce this fraction down to 4 over 1. And then when I cross multiply, I end up with 25 minus x equals 4x. I add x over, I divide by 5, and I get x equals 5. But the fact that you can set up this proportion, that's what I'm worried about. Can you set up this proportion properly? I could have done it other ways around. I could have done it as 16 over 25 minus x and x over 4 and gotten all this stuff. But the point was, I wanted to be able to reduce it. Okay, so now a new concept, a new topic, array bisector. Now this one's going to be difficult for some people, okay? What you have to understand is we are not saying these triangles are similar. It's not what I'm saying. What I am telling you is that when I have an angle bisector, I can set it up to where the side opposite, see how the red dot and the star are opposite of the congruent angles formed by the angle bisector? Those sides are proportional, along with the outer sides of the triangle. If you look at ACB as a nice big triangle like this, then the two sides that form the angle right here, those two sides are proportional to each other, along with the sides opposite here and here. So when you're setting up these proportions, you can do it in a lot of different ways. You can say AD over DB, and you can say CA over CB, or you can do the interchange the means, and you can say AD over CA, and you can do DB over CB. However you want to interchange the means. It doesn't matter if you switch these two around, but what you need to understand is these theorems and values. Make sure you know how to use them. All right, so now if we use this correctly, we could say, all right, I've got x over some number. Oh, it's 40 total. Interesting. So if it's 40 total, I could say from here to here it's 40, and then I take away the x. The other side is going to be 40 minus x. Now I set up my proportions. I like how I do this. You just kind of draw little lines as for the fractions. And I got 27 over x equals 45 over x minus 40. I'm sure you know how to use these. If you try and do this, good luck. If you mess it up, then you get the wrong answer. But make sure you're setting up your proportions that make sense, each piece corresponding to itself. Now I can cross multiply, or I can interchange the means. I would like to interchange these means because I want to get 27 over 45. And when I get that, I divide them both by 9, I get 3 over 5. Much easier to work with. Now I set up my cross multiplication. I distribute. I add 3x over. I divide by 8 to both sides. And I get x equals 15. Now that's our summary. So now when you're setting up your angle bisector problems, don't forget, we're not saying the triangles are similar. We're not